Welcome to the No-Till Training Program's 8-part webinar series. This training has been developed through a collaboration between the University of Vermont, University of Maine, and USDA Natural Resource Conservation Service. All associated work and materials are supported by the National Institute of Food and Agriculture, U.S. Department of Agriculture, through the Northeast Sustainable Agriculture Research and Education Program under subaward ENE 18-149. This webinar will focus on fertility and manure management with a presentation by Charles White. Charlie White is the new Soil Fertility and Nutrient Management Extension Specialist at Penn State. He has worked at Penn State for 10 years on various topics related to soil fertility, soil health, cover cropping, and nutrient management, and took over the Extension Specialist role in January 2018. Charlie has a master's degree in soil science from the University of Maryland and a PhD in soil science from Penn State.
All right, well, thanks everyone. I really appreciate the opportunity to be involved in this training series. No-till has really taken off in Pennsylvania, where I've been working for the last 10 years. And so I understand that up in the New England area, where a lot of you all are from, there's considerable challenges with adoption of no-till, just cooler climates, cooler temperatures. And I'm excited to see that this webinar series has been going on and this training program is going on. And I hope there's some tidbits that I can share about soil fertility management that we've learned in Pennsylvania that will translate up into the New England states as you all embark upon promoting and adopting the transition to no-till. So no-till is great for soil quality and soil health. It's great for reducing erosion. It's great for reducing energy expenditures on the farm. And in the realm of soil fertility, it does create some challenges, though, that need to be addressed. And kind of in this diagram here, what I want to convey is that under no-till management for soil fertility, there's a very limited zone of the soil that we can actually manage. So, maybe the top 1 inch or so of soil right on the soil surface, that's where we're going to be broadcasting all of our fertilizers. We're going to be broadcasting our manure. So we're going to be broadcasting our lime. And that 1 inch of soil there right at the top, that's kind of what we can manage. But the rooting depth is the whole soil profile, at least down to 6 inches and hopefully down to 12 or 24 inches if you've got that much soil there. That's what the roots are going to explore. That's where water is going to be taken up from. And we want to do as much as we can to ensure that there's good soil fertility parameters up and down at least the quote unquote old plow layer, down to 6 or 8 inches. And maybe even into the subsoil as well. So, no-till management, we're going to be broadcasting our manure, fertilizers, and lime right on the soil surface. Under tillage management, we had the opportunity to incorporate those materials, the manure, the fertilizer, the lime. It could be tilled into the soil, incorporated down to 6 or 8 inches depth. And that incorporation of those nutrients really does have some benefits in terms of being able to manage that whole plow layer. That has some benefits, and under no-till, we just need to learn to manage things a little bit differently in terms of our fertility. So there's a couple challenges that are generated under no-till management with soil fertility that we're going to talk about today. The first is the generation of an acid roof. So that's soil acidity being generated right at the soil surface. There's an issue for ammonia volatilization. When we don't incorporate manures and fertilizers into the soil, we can lose a lot of the nitrogen into the atmosphere when ammonia volatilizes. And there's issues for phosphorus stratification, very high levels of phosphorus at the soil surface. And that's right where the soil interacts with runoff water. And so there's increased risk for soluble phosphorus losses as well. So those are the main challenges and problems that can crop up for soil fertility management under a no-till system. The good thing is that these problems can all be overcome through management. Okay, it's not like these problems are an issue that we can't overcome. We just need to be aware of them and try and implement management practices that can help us overcome these challenges. So that's what I want to focus on in this presentation today. So, one of the things, because of the challenges of no-till management, of not being able to incorporate your soils, if you were in a situation where you're in the transition from a tillage system to a no-till system, before you make that ultimate commitment to going no-till, if you are going to do kind of a long-term permanent no-till, if that's your goal, that before you make that switch to no-till, while you're still doing tillage, it would really be beneficial to fix any problems that might exist in the plow layer already. So, get the soil pH measured, see if there's a lime recommendation, lime that plow layer to the optimum pH before you start the conversion to no-till. Same with any phosphorus or potassium fertility issues in your plow layer. Get those fixed through the recommended P and K fertilizer additions based on the soil test. Get that incorporated into the plow layer. And then that's going to simplify your life as you transition to no-till, and you can just manage things on the soil surface. So fix the problems that you can while you're still doing tillage before you commit to make that transition to permanent no-till, if that's what you're doing. Now, there are kind of rotational no-till strategies where you might no-till for a period of time and then you till again, and those systems have some benefits to them, and obviously that's a scenario where if 3 or 4 years later you're going to come back and do some tillage, you can help deal with issues deeper in the soil profile when you do that, when you come back and do that tillage. So there's different ways to do no-till. Some are committed long-term, never till, for the next several generations of farm family members. Other people are more in a rotational strategy. So it all depends on the setting that you're working with. Okay, so let's talk about the acid roof. So an acid roof develops primarily from the application of nitrogen fertilizers or manures, which also contain nitrogen. And when these fertilizers are added and manure is added, what happens is the ammonium form of nitrogen will nitrify. We call this the nitrification reaction, and this is a biological reaction. And in that process of the conversion of ammonium to nitrate, their acidity is generated. So you see in this chemical formula here, you see the NH4 plus, 2 molecules of that will react with 3 molecules of oxygen to produce 2 molecules of nitrate. In that process, the 8 hydrogen atoms from the ammonium are released into the soil as hydrogen protons here, which is acidity. Acidity is essentially the concentration of hydrogen ions. So most nitrogen sources are going to have some component that is in the ammonium form. So manures are going to have ammonium nitrogen. Urea fertilizer is going to pass through urea ammonium nitrate solution is going to have ammonium forms in it. So really, most forms of nitrogen are going to produce this acidity. And in a no-till system, when you're just depositing these materials on the soil surface, that acidity is going to be generated and held right at the soil surface there. Now, that poses challenges because when you take a soil sample to do a fertility analysis, you might be going 6 to 8 inches deep into the soil, and you might get a pH result back of 6.3. And depending on your target crop, the optimum pH for that target crop is 6.5. A pH of 6.3 might not be low enough to actually trigger a lime recommendation on a soil test report. Now, the reality in a no-till system is that you might have that acidity being generated right in the top 1 to 2 inches of soil there. The reality is that maybe at that surface layer there, the pH might be as low as 5.5 or something like that. And then below that, the pH is more neutral because this nitrification reaction is taking place right at the soil surface. That's where the acidity is being generated. So this is what we call the acid roof, the roof being the very top layer of the soil profile there. And certainly a pH of 5.5 is out of the optimal range. You're going to start experiencing issues, potentially aluminum toxicity, certain micronutrient deficiencies. Many of the atrazine type or triazine type herbicides are not effective at a low soil pH like this. So herbicide effectiveness is going to become an issue. So it's something that we want to pay attention to and potentially fix. So how do we pay attention and fix this scenario? What are the steps, the thought process you should go through for the acid roof? Well, the first thing is take your regular soil sample at a 6 to 8 inch depth and measure the pH and see what the lime recommendation is. So here, if we have a pH of 6.1, we might get a lime recommendation. This is just hypothetical. Lime recommendation of 2 tons per acre. And so if you get a lime recommendation from your regular soil fertility sample, then apply that recommended rate of lime to the soil surface. Since you're in a no-till system, you're not going to be incorporating that lime into the soil. You're just going to let it react on the soil surface. Now, over time, that lime will react and work its way down into the soil, through the soil profile, through the plow layer, and neutralize that acidity. Because you're not incorporating it, though, and mixing it throughout that whole profile, it will take time to reach 6 to 8 inches. It might take 10 to 15 years for lime to work its way down there. So that's one of the reasons why we say if you need a lime recommendation before transition to no-till, get that applied and incorporated, because otherwise it's going to take a long time for lime to work its way from the soil surface down to the bottom. Now, let's say you do your regular soil fertility sample and you get a pH where the pH is, say, 6.5, and the optimum for that crop might be 6.5. Well, you're not going to get a lime recommendation then. So what do? You just walk away and say, I don't need lime? Or do you start getting concerned to see whether there's an acid roof being generated? Well, you should be concerned about the acid roof. So if your regular soil fertility sample says you don't need a lime recommendation, what you should do is come back and collect another soil sample from just the top layer, 1 to 2 inches deep, and measure that with a pH spot plate to check for the development of an acid roof. So here's an example of just taking that 1 inch soil sample there from the surface. You want, just like a regular fertility sample, you want to get this from 15 to 20 locations throughout the field, mix it together in a bucket. Now, if you have a spot plate kit, so down in the lower right-hand corner here, this is just a little colorimetric kit. I think Cornell sells these. Some people call them a Cornell pH kit. But you can put soil samples in the 2 little wells here, and there's 2 different color indicating solutions that you put on the soil. And depending on the pH, the solutions will turn a certain color, and you can then check that against the card and see what the pH is in the top layer of soil. So this saves you from having to pay for another fertility test if you just do the field kit method. Now, if you do the field kit method and your 1 inch deep soil sample, it has a pH of less than 6.0, then the recommendation is to apply 1 ton per acre of limestone to the soil surface. And that 1 ton per acre to the soil surface should be enough to neutralize the acidity that's being generated right at the soil surface. And then if you just keep up with those maintenance applications of lime over the course of the no-till system, periodically every 3 years or so, check when you do your regular fertility sampling, check this 1 inch layer with the pH kit and just apply the lime to the soil surface there. You'll be controlling the acidity where it's generated. Okay, so that's it for the acid roof. I'm going to move now to talk about ammonia volatilization. So the process of ammonia volatilization is when we have nutrients in the form of ammonium, that's this NH4 plus here. Now, NH4 plus will be dissolved in the soil solution or held on the cation exchange sites of the soil. When that ammonium is exposed to a high pH, that's what this OH minus molecule here is, that's a hydroxide molecule, that high pH level will cause one of the hydrogen ions from the ammonium to pop off and combine with the OH molecule to form H2O. And then what we have left is ammonia. That's the NH3 here. And ammonia is a gas, or can become a gas. And if this reaction occurs at the soil surface, which is where we're applying our manure and applying our urea in a no-till system and we're not incorporating it, if this occurs at the soil surface, that gas is just going to volatilize off into the atmosphere and blow away. Now, ultimately, it might rain down back onto the land, but it's probably going to rain down somewhere where we don't want it. It's going to rain down in a forest, on a lake, and become a pollution issue. So so this reaction, when it occurs on the soil surface, the ammonia is highly susceptible to loss. If this gets incorporated into the soil, so if the ammonium is in the soil, actually trapped inside the soil, in soil pores, eventually that ammonia will react with water to go back to the ammonium form, and it'll be held in the soil. Now, for this volatilization process to occur, you do need to have a relatively high pH level. And this little table here shows us what percentage of the nitrogen of the ammonium fraction will be converted to ammonia based on the pH level. So if we have a neutral pH, very small fraction, only 0.5% of the nitrogen will be in the ammonia form. As we get to 8 and 9%, that percentage, or pH of 8 and 9, the percentage that will be ammonia really goes up. So this is an issue that is a combination of high pH and the ammonium form when we get the risk for ammonia losses. Now, what are the fertilizer materials that we're particularly concerned about with this? The first one is urea. And urea is a very simple organic molecule. It's an organic form of nitrogen, but it very rapidly breaks down into ammonium. That process is called hydrolysis. There's an enzyme called urease that does that conversion. In the process of urease breaking down urea into ammonium, the pH goes up to about 9, right around that fertilizer granule. That process of hydrolysis produces these hydroxyl ions, and there's a localized and temporary spike in pH up to about 9. So that's going to be a concern from the urea. Now, what about manure? Manure is another source of nitrogen where we're very concerned about volatilization losses when it's not incorporated. Manure is a source of ammonium. Originally, the manure will have a lot of urea in it, but very quickly, even on the barn floor, that urea is going to get converted to ammonium. And in the barn, there can certainly be volatilization losses. But what happens when manure is spread, it's not necessarily the urea and the manure being spread, because that urea has already been converted to ammonium. What actually happens with that manure is there's quite a bit of CO2 that's dissolved into that manure from preliminary decomposition in the manure storage. When the manure is spread in a thin surface on the soil surface, that CO2, a lot of that dissolved CO2, will raise the pH of the manure. So when CO2 is dissolved in a solution, it makes that solution a little bit more acidic. When that CO2 then gets released, the pH of that solution will become more basic. And in manure, it becomes basic enough that because of that CO2 release, that there becomes an issue for the ammonium converting into the ammonia form. This is a process that happens very quickly. You should be really thinking about trying to manage this volatilization process on the order of hours to a couple of days. That's when this process occurs, and that's when you need to manage to prevent it. It's on that quick of a time scale. This is a picture here of our research manure spreader, and we're broadcasting manure on the soil surface. And we've had graduate students study this. This is a chart from Emily Duncan's PhD dissertation from a dairy cropping system experiment that's actually funded by Northeast SARE. They measured ammonia volatilization of manure 5 minutes, 3 hours, 5 hours, 24 hours, and 48 hours after application. And they did it for broadcasted manure. They also used manure injection, which I'm going to talk about in a second. And the broadcasted manure, that's the gray bars here, you can see that most of the volatilization was occurring within 3 hours of that application of manure. After 5 hours and 24 hours and 48 hours, most of the volatilization that was going to occur had already occurred. So if you waited to the next day to come back and let's say you were still in a plow-based system, tillage-based system, if you even waited a day to come back, most of the ammonia will have already volatilized, and you're not going to get much more additional ammonia conservation by incorporating it after that point. Now they compared it to manure injection, that's the black bars here, where the manure is actually injected under the soil surface, about 3 to 4 inches deep, and the ammonia volatilization from that practice was cut down quite a bit from incorporating that. And that's because it's trapped in the soil, it has time for the ammonium to stabilize and convert back to the ammonium form and be held on the soil cation exchange sites. So just to impress upon you the impact that ammonia volatilization has on reduced availability of ammonia from manures. These are availability factors. This table here are availability factors from the Penn State Agronomy Guide. When we try and determine how much of the ammonia fraction of a manure will be available for crop use, you can see if it gets incorporated immediately, either through tillage or injection, we have 80% of the ammonium will remain available for the crop. With every day or couple days that goes by, we lose another 20% of availability of that ammonium, and that's because of the volatilization losses. So in a no-till setting, where you're not going to be incorporating, or your incorporation will be more than 7 days away, we go from 80% availability to only 10% availability. So 70% of the ammonia that would have been ammonium that would have been available, we're predicting will have volatilized without incorporation. And that's a really huge impact in terms of the efficiency of manure utilization under no-till systems, to lose that amount of nitrogen. It has some cascading effects on the phosphorus balance of soils. So if you have that much less nitrogen available from your manure, and you're putting out manure at a rate that is needed to meet the nitrogen demands of the crop, then you might have to put out double the rate of manure in a no-till system to meet the nitrogen needs for your crop, as if you were putting it out as compared to incorporating it. That means twice as much phosphorus gets added, and manures already have an uneven balance where there's more phosphorus than is needed in the manure for the crop. And so that just accelerates phosphorus accumulation in the soils in no-till settings. So it's really something to be concerned about, both for the conservation of nitrogen, but also for the balance of phosphorus. Okay, so I've mentioned manure injection a couple times. I want to show you a short little video here of just the manure injector technology that we've been using on research experiments at Penn State here. So you can see the injector moving across the field here. There's a narrow band of soil disturbance, similar to what might occur from, say, a corn planter or something like that. Essentially, at the front of this manure injector, there's a disc that creates a furrow, and then there's kind of a shoe or a tube that comes down into that furrow and injects the manure, and then there's a couple closing wheels on the back that then close that up. So we've seen a lot of benefits from this manure injection technology, and something that is considered best management practices for manure application in no-till settings. Oh, okay. So in an experiment where we've been using this at Penn State, experiment funded by Northeast SARE, it's a long-term dairy cropping system project. We've compared the nitrogen requirements for the corn crop under injection versus broadcast manure. What this chart shows is across the different years of the experiment. Those are the bars here. And then we have an average response. That's the sets of bars going across the bottom are the years, and then the average. And then we compared the nitrogen required, supplemental fertilizer nitrogen required after injection versus after broadcast manure. That's the gray bar and the red bar, left and right, injection and broadcast. So how did we determine what was the nitrogen fertilizer that was required? Well, we put out a certain amount of nitrogen as starter fertilizer, but then we came back and our side dress nitrogen rate was determined by the PSNT test. And when we incorporated the manure with injection, what we saw is that our PSNT tests tended to be a little bit higher because we had conserved more of that ammonium nitrogen. And because the PSNT test was higher, the recommended fertilizer rate ended up being lower. And so you can see across the years, every year the fertilizer that was needed under manure injection was less than the fertilizer needed under broadcasting manure. And ultimately the corn yields in each of these two treatments ended up being the same year in and year out. And so on average, corn that had manure injected needed 30 pounds per acre less nitrogen than corn that had manure broadcast on the surface. So that 30-pound reduction in nitrogen fertilizer, that's because of the improved conservation of ammonium through injection by reducing that volatilization. Okay, volatilization is not just a concern with manure, it's also a concern with fertilizer materials. And any fertilizer that has the urea, some form of urea in it, so that could be pure urea, could be urea ammonium nitrate solution, is going to be susceptible to volatilization. And as I mentioned earlier, that's because of the conversion of urea. When urea is converted to ammonium, we generate this carbonate ion here, which increases the soil pH. Now, a management practice that you can use with fertilizers to reduce volatilization is to use a urease inhibitor. So this is a product that gets coated onto the granules of urea. That's what this picture is here. It's been treated with a product called agrotane. You can see there's a very slight green tinge to this fertilizer material. That indicates it's been treated with the agrotane. It would be a pure bright white color if it hadn't been treated with agrotane. And what the urease inhibitor does is it prevents the hydrolysis of the urea, and it allows time for that urea to be soaked into the soil by rain. And typically the urease inhibitor will provide about 10 to 14 days of protection against urease. And hopefully in most climates in the Northeast, that's enough time to get a half-inch soaking rainfall to incorporate the urea into the soil so that when the urease does act on it, the ammonium will get trapped in the soil rather than volatilizing. So the active ingredient, the most common active ingredient in the urease inhibitors is NBPT, which is an acronym for this chemical formulation here. NBPT is contained in products like agrotane, agrotane ultra, agrotane plus, super U, limus. These are just different trade names of urease inhibitors. There's another type of urease inhibitor called duramide, which is a relatively new type of inhibitor. It's contained in a product called Anvil. So this is something that you should give serious consideration in a no-till system to treating any urea-based fertilizer products. This can also be mixed into urea ammonium nitrate solutions, which are a liquid form of fertilizer, or can be coated on the granule, or in the case of Super U, the granule, actually during the manufacturing process of the granule, they incorporate the NBPT right into the granule itself. These other ones are formulations that get misted onto the outside of the granule. Okay, so I mentioned you can mix these urease inhibitors into UAN solution. 50% of the nitrogen in UAN solutions is in the urea form. Another practice you can use to reduce volatilization from UAN solution is to apply that fertilizer in a band rather than broadcasting it on the soil surface. So when we broadcast it on the soil surface, we expose a very large surface area of that solution to ammonia volatilization. In contrast, if we band that application or apply it as a dribbled stream, we really limit the surface area on the soil surface that's exposed to volatilization, and much more of that product will soak into the soil where volatilization losses are protected. So the most common way to band or dribble this UAN solution on is when you're side dressing corn. So these are some pictures where we've side dressed corn, and you can see the band that's being dribbled next to the corn there, or this band is in the middle of the corn row. That's how you would want to do it. Now in no-till systems, a place that we often don't think about where UAN solution is being used is as an herbicide carrier for spring burn down applications of weeds or cover crops. A lot of farmers will use UAN solution as the herbicide carrier, which means they're putting out 60 to 65 pounds of nitrogen when they spray their burn down. And obviously in a burn down application for weeds, it's going to be a broadcast application where you're trying to get that product misted over the top of the soil surface, misted onto the foliage of the leaves. This is a very high risk for volatilization from the UAN solution, and I really strongly suggest and encourage adding a urease inhibitor to the tank mix when you're using UAN as an herbicide carrier. I think almost all of the urease inhibitors are compatible with different herbicide formulations, at least to my knowledge. And I've spoken with lots of farmers that say they've seen dramatic changes in the nitrogen availability from following their burn downs when they've started using these urease inhibitors. And it just makes sense what they're observing. It makes sense with the science that we know of the process. Okay, so that's all on the ammonia volatilization front. What I'm going to wrap up with here now is a little bit about phosphorus management. So one of the challenges with phosphorus in a no-till system is that phosphorus is a very immobile nutrient. Once that phosphate ion gets into the soil, it likes to attach itself to clay particles. It likes to react with aluminum or calcium or iron to form insoluble minerals. So if you put phosphorus right at the soil surface, it's going to tend to stick around right at the soil surface. So this is data here from deep soil profile data. So this chart here, if you see on the y-axis, it goes down. This is soil depth. So we went down past 28 inches deep, and we chunked it out into small chunks at the soil surface and larger chunks as we went down. And we measured the MELIC3 phosphorus in 2 farm fields here, are what I'm showing. This is a farm, central Pennsylvania. It's a very large dairy farm, more than 1,000 milk cows on this dairy farm. It's part of we did this work as part of a Northeast SARE project called Carbon Gaps, Nitrogen Bulges, and Phosphorus Imbalances, where we wanted to look at how different management practices like tillage or manure management, how it affected the coupled cycling of carbon, nitrogen, and phosphorus. And so this field has been in no-till for a long time, more than 20 years. And what you can see in the charts here is the phosphorus stratification. So right at the soil surface here, we see our highest levels of phosphorus. So this was about a 0 to 2 to 3 inch soil sample right at the soil surface here. We saw the highest levels, and then they start to decline through the plow layer and then even into the subsoil. Now for the MELIC3 phosphorus, which is what Pennsylvania and a bunch of other mid-Atlantic states use as their typical soil test extract, the optimum range is from 30 to 60 parts per million of phosphorus. So one of these fields is in the optimum range for the first 2 depths and a little bit below optimum in the deeper layer of the plow layer. And the other field, field 1 here, is a little bit above optimum in the first 2 increments and then in the optimum range for the lowest increment. So you can see how that stratification changes. But in both of these soils, at least some of the plow layer is in the optimum range. And when it's above the optimum range, it's not super excessive. I wouldn't call this an environmental concern. In Pennsylvania, we start to get concerned about have environmental concerns when the soil test phosphorus gets up to over 200 parts per million. So this farm is still managing things in relative balance for phosphorus. A couple ways they're able to do this is they have a corn hay rotation. So they grow about 3 years of corn silage and then 3 years of alfalfa orchard grass hay. And they add some manure to the hay phase of the rotation, but less than they do to the corn. And so during that hay rotation, they're actually mining out some of the phosphorus that they probably over-applied during the corn phase of the rotation. The other thing they do on this farm to help maintain the phosphorus balance is they use a manure solid separator. So they take out all the solid fibrous component of the manure. They recycle that as bedding back into the barns. And most of the phosphorus in the manure is contained in that solid component. So they really reduce the phosphorus content of the manure to begin with by separating out the solids. And then the last thing is, even though they're a very large dairy farm, they're an even larger crop farm. And they have several thousand acres of cropland that they're able to spread their manure across. And so even though they produce a tremendous volume of manure on the farm, they have enough land to be able to spread it on such that they're not over applying phosphorus continually on a limited land base. So those are some of the things that we saw on this particular farm that helped them maintain phosphorus levels that weren't sky high, albeit there was some degree of stratification in their soil profile with higher levels at the surface. Now, why is phosphorus stratification a potential concern? So first of all, when you put the phosphorus right at the soil surface, there's a potential for it to become unavailable to plants if the soil surface dries out right at the top. Any nutrient needs to be dissolved into the soil solution to move to the crop roots. And if the soil surface dries out, then nutrients won't move into solution and they'll become unavailable. Now, in a no-till system, hopefully you've got some residue on the soil surface, whether that's from crop residue or a cover crop mulch that's been burned down. Hopefully that's going to help maintain some soil moisture in that top layer throughout the season, more so than you would get if the soil surface was exposed. But still, the weather runs its course, and many times that layer of soil does dry out. And even if you have optimal levels of phosphorus there, if the soil is dry, it won't move to the crop roots. Now, the other area of concern is runoff of soluble phosphorus. So we're putting all of our phosphorus materials right at the soil surface. This is the same spot where surface runoff is going to be moving across the field, and there's a strong potential to dissolve soluble phosphorus. This is going to be in the orthophosphate form of PO4 3-, dissolving that out of the fertilizer materials or off of the soil itself or out of the manure and be carried off of the field. Generally, no-till is good for reducing soil erosion, and it reduces the particulate levels of phosphorus that are lost on the soil sediments that are eroded off the fields. No-till will reduce that. But what we have seen, or what a lot of people have seen, is that no-till actually increases the dissolved phosphorus of fraction. So this is data from a watershed study in Oklahoma where they compared converting from a conventional till to no-till, and they saw that the total phosphorus losses declined with no-till primarily because particulate phosphorus losses were reduced 85%. But the dissolved phosphorus losses increased. So these open circles here are where they implemented no-till, and over time, you saw that dissolved phosphorus losses got roughly 4 times as high under a no-till system as they are under a conventional tilled system. And even though the total phosphorus runoff was less, the dissolved phosphorus losses are in a form that's more potent for eutrophication. So that dissolved phosphorus can be quickly taken up by algae. And we're starting to see, have some concerns, even in areas that are dominated by no-till, there are still water quality concerns. I think the one that's most prominent would be Lake Erie. Much of Ohio is under no-till management, yet they still continue to have issues of algae blooms in Lake Erie. And it's because of this issue with the soluble phosphorus losses. This is one of the issues that's contributing to it, is the increase in soluble phosphorus losses from no-till. So what's the solution to that? How can you have your no-till cake and eat it too? I think technologies like the manure incorporation or the manure injection that I described earlier, in research we've done in our dairy cropping system experiment, we've seen that injecting the manure, getting it off of the soil surface, has led to 40% reductions in dissolved soluble phosphorus losses compared to broadcasting manure on the soil surface. So in addition to the ammonia conservation that we get from that injection, we're also seeing reduced phosphorus losses. Now, what about in a fertilizer-based situation? If you're not on a livestock farm or a farm that's using manure, what can you think about to reduce the issues of phosphorus stratification and soluble losses under fertilizer management? Well, the first thing would be, before converting to no-till, build up your plow layer to the agronomic optimum soil test P levels. It's the same issue that I described with the liming. Once you go to no-till, you're only going to be able to have impacts in the short term on that top one inch of soil or so. So if you've got a plow layer that's deficient in phosphorus, before you go to no-till, while you're still doing tillage, incorporate phosphorus fertilizer in according to the recommendations to build that up into the optimal zone. Once you've got your plow layer in the optimal zone and you're under no-till management, you're going to have to maintain your soil test phosphorus levels by replacing phosphorus at the crop removal rate. And by adding crop removal level of phosphorus fertilizer as a starter fertilizer, as a 2x2 starter fertilizer. So I'm using like monoammonium phosphate as a starter. It's a very good starter fertilizer material. You can apply that at crop removal levels, and you're getting that incorporated into the soil with the planter 2 inches deep, and then that's going to help you prevent some of the phosphorus stratification. That banding is going to enhance the availability of that phosphorus for the crop. You're going to put it right where the roots need it, and most importantly, you're going to keep it off of the soil surface where it's going to be at risk for interacting with runoff water and pose the highest risk for runoff losses. Okay, so just to sum up, there are some management concerns around soil fertility and manures that definitely create challenges when you go to no-till, but there are management practices, technologies that can help take care of these issues. It's just something you need to be aware of, and some management tweaks that you need to make to be efficient with your fertilizers and manures. So for the acid roof, lime the plow layer before converting to no-till. Continue to check for the development of an acid roof with a pH kit and apply lime to the soil surface as needed to neutralize the acidity. Ammonia volatilization, consider manure injection, consider using urease inhibitors, apply urea ammonium nitrate solution instead of broadcast spraying it. Phosphorus stratification and increased soluble phosphorus losses in runoff, consider using manure injection. Manage your manure rates and crop rotations for phosphorus balance. Some of those things that I described, the dairy farm that we sampled in central Pennsylvania, consider some of the things that they've got going on. Avoid surface application of phosphorus fertilizers, and instead consider applying it as a starter fertilizer 2x2 so it's incorporated into the soil. So I appreciate everyone listening here this afternoon.